This presentation explains the dating method for the ancient Chinese star charts. The presentation is about 55 minutes long and divided into 4 parts of approximately 15 minutes each. At the end, I will explain the star charts that Shivyukawa Harumi referred to for his observations and the creation of the star charts, which had been unknown until now. This section will give an overview of the ancient Chinese star charts. First, an overview of the dating method. Since the Kitara astronomical map, which is considered to be the oldest and most detailed astronomical map, was excavated in 2004, there has been growing interest in the date and places where the stars depicted in the Kitara astronomical map were observed. However, the astronomical map, which is a mural drawn with deforming constellation figure, has a large error, and even in a survey led by the Agency for Cultural Affairs from end of 2014, 2 types of analysis results were announced for the observation date, and the date has not been determined. This star chart is Tenshou Retsuji Bunyanozu carved on a stone monument erected in 1395 AD at the beginning of Yi Dynasty Korea. Based on the inscription engraved on the side of the drawing of the Goguryeo era, which was destroyed in 668, is believed to be the original of current star chart. For this reason, many researchers consider the Kitara astronomical map to be an astronomical map based on the star chart of the Korean peninsula. However, the inscription was written 700 years after the Kitara tumulus. Stone monuments are built for some purpose, and the contents of the inscriptions are not necessarily true. Unlike Tenshou Retsuji Bunyanozu, this star chart Koshi Gettshins handed down from the Tsuchi Mikado family was thought to be a new star chart. A magazine published in 1991 describes it as the oldest star chart in Japan, created around 1100 AD. This estimate was made in 1942 by Mr. Susumu Imato, who first discovered the star chart, based on the vernal and autumnal equinoxes in the star chart. However, this was an erroneous estimation of the precession in the opposite direction. The correct calculation is around 330 AD. This erroneous assumption remains uncorrected to this day and is not recognized as the earliest ancient star chart transcribed in China and brought to Japan before Kitara astronomical map. In this study, we clarify the origin and genealogy of ancient Chinese star charts with accurately estimated dates of original chart of the existing star charts by clarifying the method of dating. Let's consider the flow of creating a star chart. First, based on the existing star chart, observe the stars and update the star positions. Then a first version of the star chart is created based on the observed positions. Starting with this first chart, the transcription of the star chart is repeated. Some things will change in the process of this transcription, and some things will remain the same. Constellation shapes and names can change. The positions of individual stars do not change. The positions of the ecliptic and the 12th order are also copied from the chart and do not change. Therefore, by comparing the shapes and names of the constellations with multiple star charts, the relative date of the transcribed version of the star chart was determined. By calculating the precession of the position of stars, we can estimate the absolute date when the observation was made. Also, by calculating the precession of the ecliptic and the 12th order, we can estimate the absolute date when the original chart was drawn. Thus, each chart has information about 2 dates. The date the star was observed and the first chart was created, and the date it was last modified. Next, I will explain the style of the Chinese star chart. In China, longitude is measured based on 28 leading stars. For example, for the stars between Jingxiu and the next Guixiu, measure the angle to the east from the leading star of Jingxiu. The full circle is 365.25 degrees in 1 year, assuming that the angle the sun moves in 1 day is 1 degree. In the Chinese method, the angle from the vernal equinox is unknown. This method has the advantage that the reference leading star also moves with precession, so the precession is cancelled out and its influence is small. Therefore, no star observations were made for a long time to update the star chart. The latitude direction measures the angle from the North Pole as the 0 degrees. The latitude of the equator is about 91.5 degrees, and the South Pole is about 183 degrees. In the Chinese constellation, there were three independent constellation system of Mr. Seki, Mr. Kong, and Mr. Fu in the Han Dynasty. It is said that these three constellation systems were combined into one by Chenzhou, the person who ruled Wu's astronomy during the Three Kingdoms to Jin Dynasty period, and created a star chart. The star chart after that consists of three constellation systems. Also, as a way to organize the constellations based on the star area are changed, from the 5 gans in the era of Hanchu, to the system of Middle Kan, 28 Chiku, Outer Gan in Jinshu, finally Sainan 28 Chiku. Thus, the Chinese constellation underwent a major change during the Jin dynasty. After Chenzhou, the Song dynasty Senrikshi in the 5th century northern and southern dynasties made copper celestial globes with 3 constellation systems in 3 colors based on Chenzhou's classification. This color coding was passed down to the Tang dynasty, and the Dunhuang astronomical chart is also color-coded. The armillary sphere in the photo is a bronze celestial globe left at the old observatory in Beijing. All existing Chinese charts, including the Kittara chart, consist of 3 constellation systems. The charts consisting of the 3 constellation systems do not exist before Chenzhou, so the date estimate for the star observations and first edition charts of those charts are limited up to the end of 3rd century AD. If the estimated date is older than this, there is a problem with the estimation method or data. The major difference between Chinese and Western constellations is the number of constellations and stars. The number of constellations in China is about 280, about 6 times that of the Western, and the number of stars that make up the constellations is about 1,500, which is 1.5 times more. Since the number of bright stars in the starry sky is limited, about 500 stars, which is the difference in the number of stars, will be faint stars of 5th and 6th magnitude. There are no bright stars in the ancient North Pole. The ancient pole star is included among these faint stars. Also, in China, there is no classification of magnitude based on the brightness of stars, and there is no difference in the size of stars drawn on star charts. There are 2 methods of drawing Chinese star charts, circular charts and rectangular square charts. First, in the case of a circular chart, draw all the stars on a circular chart with the celestial North Pole as the center. There are 3 concentric circles centered on the North Pole in the circular star map. The inner circle is Nike, and the inside of the circle is the star that can always be seen from the observation site. The middle circle is the equator. The outer circle represents Geki, and this outer star cannot be seen from the observing site. The eccentric circle, which is about 23 degrees off the center of the equatorial circle in the direction of the winter solstice, is the ecliptic, which is the path along which the sun passes. This chart is suitable for observing comets that pass near the North Pole. I will briefly explain Nike and Geki here. The inner circle, Nike, is a circle centered at the celestial North Pole and with a radius equal to the observer's latitude. The star in the inner circle never sets below the horizon. The outer circle, Geki, is also a circle drawn centering on the South Pole. Contrary to inner circle, the star in the outer circle is always below the horizon and invisible to observer. In the case of a square chart, the inside of inner circle is drawn as a circular chart. A square chart is drawn from Nike to Geki. Unlike the Mercator projection, the width of 1 degree latitude does not change. The square view is suitable for observing celestial bodies moving near the ecliptic, such as the moon, sun, and planets. This is example of Koshi Gettshins, which is a square star chart. As the lines of longitude shown in orange corresponding to the area of 28 Shuku. The lines of longitude indicated in yellow of the 12th order corresponding to the 12 western signs, so they are drawn at approximately every 31 degrees. Stars from inner circles latitude 35 degrees to outer circles 148 degrees are drawn. The calculated observation site is 34.4 degrees north latitude, and it is thought that Yangcheng, the reference site of the Chinese calendar, is assumed to be the reference observation point. Therefore, it is not possible to estimate the observation site of the stars from inner circle and outer circle. Yangcheng, which is about 60 kilometers southeast of Luoyang, there was an instrument to measure the length of the sun's shadow in the ancient Zhou period, and it is said that it was used as a reference for calendars such as the winter solstice. As a result, this area became the center of the country and the reference site for calendar. Next, I will briefly introduce ancient Chinese star charts that have been handed down to the present day. This star chart is the Koshi Gettshins inherited by the Tsuchi Mikado family, which I explained earlier. This is a transcribed chart from the original chart by Yasuo Abe around 1317 AD. Although it was burned out in an air raid during the war, the photograph remains. A line is drawn every 1 degree in the square drawing, that looks like it was drawn on modern graph paper. This is also one of the reasons why it was not thought to be an old star chart. However, the grid map was proposed as a cartographic principle by the 3rd century Shin geographer Peixiu. Since it is drawn on graph paper, the positions of the stars are accurately recorded and can be read, so it is a star chart that is as valuable as a star position table. The figure on the left is a picture of 28 constellations drawn on the ceiling of the stone chamber of Takamatsuzuka tumulus. It was discovered and excavated in 1972. There are 28 constellations drawn around the constellation of North Pole and the Shiho. In addition, the reconstruction drawing on the right, which seems to have been attached to the original excavation report, is also used in a recently published book. However, the part enclosed in the red square is not in the left figure, and the restoration contents are almost wrong. For example, the cross-shaped Goishiu in the left figure is square in the right figure. Also, the north and south directions of other constellations are reversed. When examining an excavated astronomical map, it is necessary to examine the map as it is. The Kittara astronomical chart on the left is an astronomical map drawn on the ceiling of the Kittara burial mound. It was discovered in 1998 and excavated in 2004. About 74 constellations and 350 stars are drawn around the pole star. The number of original Chinese constellations on the right is over 280, and the number of stars is over 1,500. Therefore, the Kittara astronomical map is a fresco drawn with about 1/4 of the deformed constellations. This is a superimposition of the Kittara astronomical chart and the original Chinese star chart. The ecliptic in the Kittara astronomical chart is incorrectly drawn as almost symmetrical. Geiki is about 45 degrees north latitude, and the original constellations around Geiki are not drawn except for the Old Man star. It is also said that Nike came from the Korean peninsula because it coincides with the latitude of the Korean peninsula at 38 degrees, but there is no evidence that only Nike was drawn accurately. Furthermore, in order to fill the screen with fewer constellations, the constellations are enlarged and spaced out. For these reasons, it can be said that this astronomical map does not consider accuracy. Among them, the 28 constellations are not deformed and retain their shape, and the Kittara astronomical chart is also an astronomical chart that focuses on the 28 constellations centered on the pole star. In 1900, a large number of documents were discovered in the Majao grottos in Dunhuang, and British explorer, Stein bought some of them and brought them back to the British Museum. Science historian Needham found the astronomical chart in the documents and introduced it as Dunhuang astronomical chart. This astronomical chart is a transcribed version of the square star chart, similar to Koshi Gettshins, divided into 12 orders for each month. Needham dates it to around 940 AD, but does not provide no evidence for this. The Dunhuang astronomical map is color-coded with 3 colors, red, black, and a black frame only. Compared to Koshi Gettshins on the right are colored, it can be seen that Dunhuang astronomical map is a chart similar to Koshi Gettshins, even if you look only at this inner circle part. Comparing the two charts reveals the error. The Emperor is a mistake in the constellation of Gajio. There is a name of the constellation Gushin, but there is no figure of the constellation. In addition, there are two Tenichi Taichi, one of which is Nichu's mistake. Some papers say that the pole star is not drawn in the Dunhuang astronomical map, but looking at the image, there are 5 stars in a row, which is constellation of North Pole, and its 5th star surrounded by the constellation of Sifu is the pole star. The Tencho Retsuji Bunyanozu is the stone-carved star map that I explained earlier. The size of inner circle is expanded according to the latitude of the Korean peninsula, but the size of outer circle is 33.1 degrees, which is close to the latitude as it was introduced from China. Canopus is said to be the old man's star, but if you observe it at a latitude of 37.7 degrees on the Korean peninsula, you can't see it because it is on the outer circle line. In addition, it should be noted that many original modifications were made to the star map during the Goryeo dynasty after it was introduced from China. For example, the constellation Arrow has 2 arrows, but only one in the Chinese star chart. And the Hakaku is a rectangular constellation with a handle in along with internal circle, but in this chart, it is tilted 90 degrees and changed to a pentagon with a handle. Susong astronomical chart is a square star chart created by Susong, an astronomer from the northern Song dynasty of China, and was published in the book in the Tianyu era around 1090. It is said to have been drawn based on observations made during Yuanfeng era around 1080. The Suzhou astronomical chart is also known as the Junyu astronomical chart. Based on the star map produced by Koshao in the northern Song dynasty around 1190 AD, this is a stone-carved star map produced by Uqin in 1247 AD during the reign of Junyu. This star chart is also presumed to be based on observations made during the Yuanfeng period around 1080 AD. The latitude of Suzhou is about 31 degrees. It is thought that this star map is also drawn centering on Yangcheng, which is the standard site of the calendar. From here, dating by the shape and name of the constellation, you can see when the last revision of the original chart was made. First, how to distinguish between Tang dynasty and Song dynasty star charts. At the beginning of the Showa era, Mr. Ogawa investigated the records of stellar occultations and found that the constellation known as the Crying Star was replaced by the constellation Libijin after the 11th century. The feature of the star charts from the Song dynasty is that the constellation Libijin swallows the constellation Crying Star and extends to the Susiu. Koshi Gettshins on the left is a star map of the Tang dynasty because it remains in Weishiu, a crying star is ahead. The Susong astronomical chart on the right, extends to Susiu, so it can be presumed to be a star chart from the Song dynasty. Tenchao Retsuji Bunyanozu is in Weishiu, so it is a Tang dynasty star chart. The Suzhou astronomical chart extends to Susiu, so it is a star chart from the Song dynasty. The Dunhuang astronomical chart is divided into 12 descriptions, so it is not certain, but it is thought to be a star chart from the Tang dynasty because the shape of the constellation is similar to Koshi Gettshins. In addition, the 12th order range is written next to each chart. The 12th order range of the Dunhuang astronomical chart is the same value as Kaiwan Zhanjing, a book of astrology compiled in the Kaiwan period of Tang dynasty around 720 AD. Therefore, it can be assumed that the Dunhuang astronomical chart is a copy of a star chart after the Kaiwan period onwards. Based on the above, there are 3 star charts based on the Tang dynasty original charts, the Dunhuang astronomical chart, the Koshi Gettshins, and the Tenchao Retsuji Bunyanozu, excluding the wall paintings of the ancient tombs. From here, it is an dating of the star chart by the shape of the constellation. The first is the shape of the Yishiu. The Yishiu of the Kitara tumulus around 700 AD was a constellation that was 3 parts. Koshi Gettshins is the same. Takamatsu Suzuka map is not clear because the central part is missing, but the remaining upper and lower parts overlap with the Kitara astronomical chart. When this becomes the rightmost Song dynasty, the top and bottom are connected and become one. The form of Tenchao Retsuji Bunyanozu is almost the same as that of the Song dynasty. The Dunhuang astronomical chart in the middle is still 3 parts, but it looks like it's about to connect. Next is the shape of Tianyuan. Koshi Gettshins is a combination of W and M, and can be seen at the edge of the river. In the Song dynasty on the far right, the vertices of W and M are connected, and the shape has changed to a line extending in 4 directions from the hexagonal key in the center. The shape in Tenchao Retsuji Bunyonozu is the same as that of the Song dynasty. The Dunhuang astronomical chart in the middle is a hexagonal key surrounded by a square. This is also considered to be a form derived from Koshi Gettshins. Next is the shape of the Tianjiang Jun. Koshi Gettshins and Dunhuang astronomical charts are horizontal compositions. The Song dynasty on the right has changed to a vertical composition. Tianjiang Jun in Tenchao Retsuji Bunyonozu is also vertically oriented, almost the same as the composition of the Song dynasty. Next is the form of Jinqiu. The charts of the Tang dynasty on the left has only 2 vertical lines connecting the stars, and no horizontal lines. In the Song dynasty on the far right, there are 2 horizontal lines, forming an shape of sharp. There is only 1 horizontal line in Jinqiu of Tenchao Retsuji Bunyonozu in the center. Next is the shape of the Guishiu. Koshi Gettshins and Takamatsuzuka Tumula Sishukozu are in the shape of a cross. In other star charts, the central star is surrounded by a square. The cross shape of the Guishiu appears to have been used only in the early Tang dynasty. Next, I will explain the changes in the shape of the constellations due to the difference of the pole star. It is widely accepted that the ancient pole star was the star Tihoshi, which means emperor star, but this is a mistaken identification in modern times. This error is evident in the ancient star chart we will discuss below. In China, since the Chunkai period at the latest, the star closest to the celestial pole has been regarded as the pole star. Confucius called pole star of HR 4927 as Hoku Shin. In the Jin dynasty around 300 AD, HR 4852 was in the center of the sky and was the pole star. Since the Sui dynasty, HR 4893 has been used as the pole star for survey, but the pole star in the star charts created by copying old star charts remained the old pole star for a while. Around 300 AD in the left figure, the pole star HR 4852 was center of the sky, and 5 stars of the constellation named North Pole were almost aligned. In the figure on the right, in Song dynasty, the pole star has changed to HR 4893, which was one of the stars in the constellation Suho, so 5 stars of constellation North Pole are lined curve. In the Tang dynasty chart on the left, the 5 stars of constellation North Pole are all lined in a straight line. In contrast, in the chart on the right, the 5 stars of constellation North Pole are curved. The line connecting the 4 stars other than the pole star is quite far from the pole star. Tenchao Retsuji Bunyonozu is also almost identical to the Song dynasty form. This is probably because the new pole star HR 4893 was start to draw at the end of the Tang dynasty. Next up are Swanyan and Guan, the distinctive constellations of Koshi Gettshins. There is no number on the star in the squared part of Swanyan. This was added later by someone who found it odd compared to the constellations in the other star book. The Swanyan's tail in Koshi Gettshins runs horizontally to the west, but in other charts it runs in a northwest direction, like the added tail. And the square constellation circled at the bottom is the constellation Guan. It means the beacon tower. There are 5th magnitude stars that can be identified in this constellation as shown in the right figure. This constellation is north of Guishiu on other star charts. Therefore, in later star charts, the constellations moved in the direction of the arrows. This makes Koshi Gettshins the oldest of the Tang dynasty charts. These shapes in Koshi Gettshins match the description of the shape of the constellation described in Kaiwen Zhanjing. Therefore, other star charts are considered to more than 1 generation newer than the age of Kaiwen Zhanjing. This table summarizes the changes in the shape of the constellations. The orange part is a feature of early Tang dynasty star charts. Yellow is the Tang dynasty star charts. Green can be said to be a feature of Song dynasty star charts. From this, it is clear that Tenchao Retsuji Bunyanozu is a star chart located on the boundary between the Tang and Song dynasties. Excluding the mural paintings of the ancient tombs, which are known to have been produced around the year 700, based on this table, they are Koshi Gettshins, Dunhuang astronomical maps, and Tenchao Retsuji Bunyanozu, in descending order. Also, from the shape of the Guishiu, it is possible that the Takamatsu Suzuka map was modeled on a drawing older than the Kitara astronomical chart. In China, from the middle of the 8th century to the 12th century, several maps of 28 constellations were found on the ceilings of tomb chambers. We will check the shape of those constellation map here. In addition, no map of the 28 constellations has been found on the Korean peninsula during this period. Therefore, the maps of the Takamatsu Suzuka and Kitara tumulus, which were constructed around 700 AD, are unique and the oldest star map in the world, based on the concept of destiny centering on the pole star. This is a map of 28 constellations painted on the ceiling of a tomb chamber in the middle of the 8th century in the Astana burial mounds in Turpan. The design is extremely abstract, so it's not very helpful, but Yishiu is represented by the letter U. The Jingshiu is tied at the ends with a line. Guishiu is square. This is map of the 28 constellation in the tomb of the Goitsukoku royal family in southeastern China, dating 900 AD, which is the oldest map keeping the constellation shape in China. The shape of the constellation is slightly older than Tenchao Retsuji Bunyanozu, with Yishiu connected, Jingshiu has only in vertical lines, and Guishiu in squares. It is the oldest constellation map with a clear date, where the connection of Yishiu can be confirmed. Based on these drawings, it can be assumed that the original drawing of Tenchao Retsuji Bunyanozu, to which Yishiu is connected, is also a drawing made at the end of the Tang dynasty around 900. This is the 28 constellation map about half a century later, in the same Goitsukoku royal tomb. Yishiu uses the composition of the three-part style. Others are the same. 5 stars constellation of North Pole is curved. This is the 28 constellations map painted on the ceiling of Goryeo tomb in the 5 dynasties period. Yishiu is 3-part style, but it is extending up and down from the center. Jingshiu has 1 horizontal line. Guishiu is square. This is a 28 constellations map drawn on the lid of a can containing an epitaph, around 940, in the early southern Tang dynasty, in central China during the same period of the 5 dynasties. You can see that the Yishiu is connected. Jingshiu has 3 horizontal lines, but it seems that it was already in shape of sharp at this time. Guishiu is square. This is a 28 constellation map in the tomb of the Liao, who ruled northern China, mainly in Inner Mongolia. Yishiu remains divided into 3. This 3-division design remained even in the period of Song dynasty. Jingshiu is shape of sharp with 2 horizontal lines. Guishiu is square. From the 28 constellation maps of the tomb chamber above, it can be confirmed that the Yishiu was connected and the Jingshiu began to change to shape of sharp in the early 900 at the end of the Tang dynasty. Based on the above study, the figure below shows a tentative restored map of Takamatsu Suzuka map around 700. The current one is shape at Song dynasty. Next is dating by constellation names. The constellations that were regarded as Guki in Koshi Gettshins and Dunhuang astronomical maps have changed to Yuki in the Tenchao Retsuji Bunyanozu. Constellations that are regarded as Tianxi in Koshi Gettshins and Tenchao Retsuji Bunyanozu are replaced by Shi in the Suzhou astronomical chart. Shi, often introduced as the name of a Chinese constellation, is actually a relatively new name. This table summarizes the changes in constellation names. In the Tang dynasty, the constellation was called Guki, but in the Song dynasty it changed to Yuki. Here again, we can see that Tenchao Retsuji Bunyanozu is the star chart close to the Song dynasty. Also, the constellation that was Tianxi in the Tang dynasty changed to Shi in the Song dynasty. This is considered to be the influence of Fatanka, an astronomical poem. Fatanka is believed to have been written by a man of the Sui dynasty, but this table tells us that Fatanka was a poem from the late Tang dynasty. In addition, it is presumed that the change of character of Huben and Tianyuan in Koshi Gettshins was due to taboo, as were the Book of Jin and Sui compiled around the same time. Taboo is a practice that forbids the use of name of the monarch or his relatives, and it is an important factor in the dating of ancient Chinese documents. In Koshi Gettshins, the use of tiger and UN is restricted, and men is used. The use of tiger and UN was prohibited after the accession of Gao Ziu, and the use of min was prohibited after the death of Taizong. This condition matches the situation of Koshi Gettshins from 618, when Gao Ziu ascended the throne, to 649, when Taizong died. Koshi Gettshins was transcribed from Old Star Chart during this period, and was brought to Japan as the latest star chart. It was announced in 2009 that the Dunhuang astronomical map was estimated to be dated from 649 to 683, based on the character of Min in the section of future forecast by cloud in the first half of the scroll. However, the characters for tiger and UN, whose use was restricted during this period, are used in the second half of the star chart, so it is thought that the first half of the forecast by cloud and the second half of the star chart were written in different years. The Dunhuang astronomical map contains many typographical errors, and the title is still unknown. However, the title can be read as a detailed interpretation of celestial phenomena and a book of cloud forecast, and it is thought that two diviners' books of different times, forecast by cloud and forecast by heaven, were transcribed into one scroll. Judging from the changes in the shapes and names of the constellations above, the estimated date of the direct original map of the star map are follows. Koshi Gettshins is from 618 to 649 due to the situation of taboo. This estimation is also consistent with the shapes and names of the constellations. The Dunhuang astronomical chart is dated around 800, which is newer than Kaiwen Zhanjing because the value of 12th order are the same and the shape of the constellations is newer than Kaiwen Zhanjing generation. Tenchao Retsuji Bunyanozu is close to the Song dynasty, and is estimated to be around 900 at the end of the Tang dynasty. And from the other modifications left on the chart, it is presumed that the original chart came from China in the early Goryeo dynasty at 900s, was used and revised several times in the Goryeo dynasty. In this way, the constellation shapes and names are traces of the period in which the direct original star chart was drawn. However, there is no trace of the original drawing in the Tenchao Retsuji Bunyanozu that dates back to the Goguryeo period, which is indicated in the inscription. From here on, we estimate the date based on the positions of the stars. The method of least squares is a method of finding the most probable relational expression by minimizing the sum of the squares of the errors. In the case of the Western Star Catalog, the equatorial longitude is the absolute value from the vernal equinox, so the year that minimizes the error in the following formula will be the center year of the estimated measurement year. The declination method is the year when the error of declination is the minimum, and the right ascension method is the year when the error of right ascension is the minimum. The declination and ascension method is the year in which the angle between the observed and theoretical values is minimal. In the case of the Chinese star catalog, the absolute position in the right ascension is not determined because the equatorial longitude is the angle from the leading star. Therefore, the equatorial longitude is compared by the width of house between the leading stars. In this case, the precession is cancelled and the change is small. Declination is the same way as in the Western catalog. This is a date estimation for Koshi Gettshins. The graph shows the cumulative error of 28 stars. In the declination method, the accumulated error changes in V-shape. In comparison, the house width method expands the estimated years because there is little change. In the case of the Kitara astronomical map, which is a design mural, the error is very large compared to the accurate star chart Koshi Gettshins, so the spread of estimated years is also large. Even in the case of Chinese star catalogs, if the right ascension can be assumed, Dates can be estimated in the same way as in the Western catalogs. Tsugo Nakamura devised the 28 constellation bootstrap method, which uses each leading star as a temporary reference point, longitude 0 degrees, to determine the estimated year, and takes the average of 28 estimated years as the final estimated year. Since the bootstrap method, which is a statistical calculation method, is not used here, this method is simply called the declination and estimated right ascension method. This is an explanation of how to set each leading star as a temporary reference point, 0 degrees right ascension. For example, in the case of Koshi Gettshins, the size of the house is known, as shown in the light blue column. First of all, if Jiaoxiu is the reference point, the right ascension of Jiaoxiu is 0 degrees and the right ascension of Kangxiu is 12 degrees. Of course, the theoretical value of the Jiaoxiu leading star is shift and set to 0 degrees right ascension. By moving the calculation year under this condition, the year that minimizes the error can be calculated. Then, based on next Kangxiu, calculate the year with the smallest error. From the 28 estimated years obtained in this way, the average is taken as the final estimated year, and the deviation of the estimated year can be also calculated. This is a graph of simulations of measurement errors and deviations from the estimated center when each estimation method is used. If there is a large error in observation or drawing, the estimated range will be widened. For example, in the star chart with an error of 2 degrees, in the case of the longitude width method, the range is about plus or minus 460 years from the center, making it almost unusable as an estimation method. In the declination method, it is about plus or minus 100 years. Based on the Western method, the best result is about plus or minus 10 years. It can be seen that even with the declination and estimated right ascension method, it is subsided to about half of the declination method. This table is the result of calculating the ancient star chart by each estimation method. It can be seen that the Tang dynasty star chart was measured around 400 AD. And the Song dynasty star chart was measured around 1100 AD. Among these star charts, Koshi Gettshins drawn on graph paper is the most accurate star chart. Next, I will explain the dating based on the vernal and autumnal equinox points. The vernal and autumnal equinoxes are the points where the equator meets the ecliptic, the path of the sun. In Chinese circular charts, the equatorial and ecliptic circles are drawn with the same radius. So, the vernal and autumnal equinoxes are not facing each other with 180 degrees. Therefore, correction is required only for theta in this figure. After applying this correction, the estimated years are 327 years for Koshi Gettshins, 367 years for Tenshou Retsuji Bunyanozu, and 359 years for the Suzhou astronomical chart. As a result, the ecliptic lines drawn in the star charts in the 300s were passed down to the Song dynasty over the Tang dynasty. Next, I will explain the dating by the 12th order. The 12th order divides the celestial sphere into 12, like the Western 12 signs. In the 12th order based on seasons, the midpoint of one of the 12th order, Siki, is the winter solstice. In Koshi Gettshins, the midpoint of Siki is at 22.5 degrees of Doshiu. This coincides with the winter solstice in 163 BC. Mr. Ozaka CG puts the estimated year by the 12th orders to 190 BC and the estimated year by the position of the stars to around 500 AD. He described Koshi Gettshins as a mysterious star chart which has two epochs. But there was a reason for this. This table shows the location of the winter solstice in ancient calendar systems. This figure shows the position of the calendar's winter solstice as a triangulation point. Until Keshoriki, the winter solstice was almost at around 21.5 degrees of Doshiu. Since Keshoriki was in force until 451 AD, it is almost consistent with the position of the winter solstice in Koshi Gettshins. As a result, the 12th order, which was estimated to be 163 BC, is also consistent with the estimated stellar observation date around 400 AD. In this way, there is a relationship between the calendar system and ancient star charts, and it is believed that the reference points of the inner and outer circles are also based on the calendar system. Star charts after Koshi Gettshins are 12th order based on the astrology called field theory, and cannot be used for dating. Here, I will summarize the estimated date of Koshi Gettshins. This table summarizes the published dates of Koshi Gettshins. No estimated age has been established so far. Mr. Ozaki CG deduced that it was the world's oldest calibrated star chart, possibly dating to Eastern Jin, but it was not yet accepted by researchers. The results of several estimation methods, such as the vernal and autumnal equinox points, the 12th order, and the positions of stars, which I have explained so far, are almost consistent in date. It has become clear that Koshi Gettshins is based on the original star chart drawn by observations from the mid-300s to around 400s during the Eastern Jin dynasty. Based on the above results, this is an estimated history of Koshi Gettshins. First, star observations were made in the latter half of 300s, probably based on Chenzhou's star charts, and the first star charts based on them were produced. Next, between 618 and 649, the original star chart of the Koshi Gettshins was transcribed in China, based on the first star chart or a star chart that was copied from it. It is believed that the star chart was brought to Japan in the Asuka period soon after it was produced. As a result, azimuth survey and time measurement using the stars became possible even in Japan. The true north-oriented palace was started to build from around 640, and it is believed that Koshi Gettshins was introduced in 632 when the envoy to Tang China returned to Japan. Based on that star chart, a star chart transcribed around 1317 AD existed until the early Showa period, and there are photographs left. There is a star named Tenno in the Koshi Gettshins, and it is said that Tenno is the center of the heavens and is the god of East. This is enough description to adopt Tenno in Japan, east of China, as the name corresponding to the Emperor of China. Here, we will summarize the results of estimating the date of production of the star chart that became the basis of the ancient star chart that remains today. An analysis of the positions of stars and the others in Tang dynasty star charts suggests that the stars in these charts were most likely observed in last half of 300s AD and first chart was made. As for the estimated date of the Kitara astronomical map mentioned at the beginning, the estimated date of 300 plus or minus 90 AD by Mr. Soma is close to the result. This table summarizes the date estimates for ancient Chinese star charts. Based on the estimation of the orange part, it can be assumed that the original chart of the first edition was produced based on observation data in the last half of 300s AD. Based on that star chart, the star chart that was transcribed in the early Tang dynasty is the Koshi Gettshins. The Koshi Gettshins is considered to be the most faithful representation of the original star chart. The ecliptic line in the Suzhou astronomical map is thought to be a copy from the star chart of the Tang dynasty that was used as an original. In this way, by comparing the star charts side by side, it can be concluded that the origin of all ancient star charts in China is the star charts produced during the Jin dynasty after Chenzhou, who integrate 3 constellation systems. The dating the star chart by numerical calculation using precession only confirm this. Therefore, dating by the name and shape in the green area is important to know their position in the star chart family tree. The Book of Jin contains many records of occultations by the moon and planets, and it was a time when astronomical observations were actively carried out. Chenzhou of Wu, who compiled constellations and created star chart, also served as an astronomer in Jin after the fall of Wu. Based on Chenzhou's star chart, an accurate star chart based on observations was born. This figure summarizes the family of star charts based on the dating results described above. First, in the 300s, stellar observations were made based on Chenzhou's star chart, and the first star chart based on this was produced. Based on that star chart or a star chart that was copied from it, the Koshi Gettshins was transcribed in the early Tang dynasty. It will be a star chart that conveys many of the features of the 4th century star chart. The Kitara astronomical map is a mural design modeled on the star charts of the early Tang dynasty, such as Koshi Gettshins. The Dunhuang astronomical chart is a copy of a star chart from the Middle Tang dynasty. The original chart of Tenchao Retsuji Bunyanozu is a chart of the late Tang dynasty that was brought to Korea from China in Goryeo. Star observations to create a star map were not performed after the Jin dynasty, but only after the Song dynasty. Therefore, all ancient Chinese star charts have their roots in China in the 300s AD. In addition, the original chart of Tenchao Retsuji Bunyanozu is not the Goguryeo star chart that was described on the inscription, but the star chart of China at the end of the Tang dynasty. There is no longer any evidence that the original star charts of ancient tombs, such as the Kitara astronomical map, came to Japan via the Korean peninsula. Therefore, it is believed that the astronomical knowledge and techniques of the Asuka period came directly from China after the dispatch of envoys to Tang in 630. This figure shows the consistency between the direction of the ruins of the capital palace and the direction measured by pole star, which was explained in the previous day. It was after first mission to Tang dynasty that the true north-oriented palace by this measurement method began. The first palace with a true north direction is believed to be the Kutara Palace of Emperor Jomei in 639, but it has not yet been discovered. According to Sinu's Chuan city planning, the true north direction capital city is the stage for dynastic ceremonies that embody the existence of the destiny and prove the legitimacy of those in power on earth. This Hokushin's introduction of the ideology of destiny is the reason why the god of pole star appears at the beginning of the Kojiki as the god of the highest rank. Further supporting the introduction of the Tang's ideology of destiny and astronomical technology during this period is the existence of the Koshi Gettshins, which was produced in China during the same period, and there is a possibility that Tenno have been named by this chart. We compared and examined the dates of existing Chinese ancient star chart using methods such as the shapes and names of constellations and the positions of stars and the ecliptic. As a result, it became clear that the origin of existing all ancient Chinese star charts is observation-based star chart of the late 3rd century, following Chenzhou, which integrated the 3 constellation systems. Koshi Gettshins is the oldest star chart that best conveys the characteristics of the star charts of the Jin dynasty. But his value was not understood, due to the lack of accurate dating. Koshi Gettshins is more accurate than other ancient star charts and has scientific value. The study of ancient Chinese star charts would not be possible without Koshi Gettshins. It is hoped that it will be preserved and restored as a World Heritage by a public institution. This concludes the presentation of the dating method for ancient Chinese star charts. Shivyukawa Harumi compiled Joki Ariki to replace Senmai Orki, but he also conducted star observations, identified stars in Chinese constellations, and left star charts and celestial globes. However, the star chart he referred to during his observations and production of the star chart were unknown until now. Here we clarify it. Harumi created star charts in 1670 and 1677 based on the star chart Tenchao Retsuji Bunyanozu of Yi Dynasty Korea. For this reason, there is a notion that all of Harumi's star charts are based on Yi Dynasty's star charts, but this is actually not the case. Tenchao Retsuji Bunyanozu is a star chart carved in stone, and based on it, a woodblock star chart was created in 1571. It turned out that Harumi had referred to this woodblock star map, not the rubbed copy of the stone-carved star map, based on the error in the position of the leading stars. Some say that Harumi created the star chart by imitating Tenchao Retsuji Bunyanozu, but in reality, he corrected 4 of the 7 errors in the leading stars at the time of the first star chart. After compiling the Jokia calendar in 1684, Harumi began observing the stars, and in 1690, about 10 years after the second star chart, he created a celestial globe reflecting his own observations. In 1698, he published a star chart and star catalogue that compiled his observations in his book Tenman Kaito. These have almost no influence of the Yi dynasty star map. The following year, in 1699, Harumi published his last star chart Tenman Sizu under the name of his son. The contents are the same as the star chart of Tenman Kaito which he produced the previous year. This is a comparison of the characteristics of Tenshou Retsuji Bunyanozu with other star charts. The 4 columns on the right are Harumi's star charts. The yellow part is the characteristic of Tenshou Retsuji Bunyanozu. Harumi's first chart has many characteristics of Tenshou Retsuji Bunyanozu, but in the second chart it fades and eventually almost disappears. Comparing his star charts, the composition of the constellation Sokoku means countries in the first and second star charts was completely different. The Sokoku in the second star chart are similar to the Yuan dynasty star chart. It is thought that Harumi had obtained this Yuan dynasty star chart before making the second star chart. The format of Harumi's star catalogue is the same as that of the Yuan dynasty, in which the coordinates are written in the constellation figure, which proves that it was obtained. This is the comparison result between Harumi's star catalogue and the Yuan dynasty star catalogue. The 2 star catalogues show a strong correlation. However, this catalogue does not actually exist in Japan at present. This is a star chart at Rinshō-in, a temple in Kyoto, dedicated in 1636 by the 3rd shogun Iemitsu. This star chart was presented by the Joseon envoys, but it is based on the star chart of the Ming dynasty in China. As a result of comparison, I found that the Nike part of Harumi's last chart uses this chart. This is a comparison of Harumi's Tenman Saisho and the star chart of Rinshō-in temple. The solid line is Harumi's chart. The dotted line is the Rinshō-in chart. Harumi's observation data are also included, so there are some differences, but it is clear that Harumi made observations and created the star chart with reference to this Rinshō-in star chart. Also, Harumi replaces the Tang dynasty pole star with the modern pole star. This figure is the genealogy of Harumi's chart of stars. Harumi made 3 star charts. The first and his second star charts are based on Woodcut Tenshou Retsuji Bunyanozu. Harumi also made a celestial globe after his observations in Kyoto. After his observations in Edo, he compiled the 3rd star chart and star catalogue. Harumi left no record of the process of creating the star chart, and most of the literature has been lost, so it was unknown which star chart was used for observations. A comparison with the Yuan dynasty star table revealed that he had obtained the Yuan dynasty star table before making the second star chart. In addition, by comparing the Nike part of the drawing, it is thought that before starting observations in Kyoto, he also obtained a copy of the star chart of Rinshō-in temple, based on the star chart of the Ming dynasty. It is believed that he also had the Suzhou astronomical chart, which is relatively easy to obtain. Until now, it has been thought that the star charts produced by Harumi were influenced by the star charts of Yi dynasty Korea, but in fact, the latter half was influenced by the star charts of mainland China from the Song dynasty to the Ming dynasty. Also, judging from the characteristics of Harumi's star charts, it seems that he had not seen Koshi Gettshins. This table shows the estimated observation date of Harumi's star catalogue by the least squares method. The results other than 28 stars indicate that Harumi himself actually observed the position of stars. Modern Chinese constellation maps are based on the identification of missionaries active in China from the late 16th century onwards. It is thought that they made the identification based on Western star charts and star catalogues, which have fewer stars at that time, so the reliability of the identification is low. Therefore, Harumi is considered to be the last person to identify the constellations drawn on the ancient Chinese star chart by the actual observation. This concludes today's presentation. Thank you very much.